So let's talk a little bit about actually finding a cycle inside of a graph and the general process of this. To set this up, I'm going to create a new class called graph, and we're going to do basically the same sort of setup that we saw in previous videos, where we're going to have an initialization. And the initialization is actually going to require two things this time. We're going to keep track of the number of vertices in our graph, which I'm going to call v. And I'm going to keep track of the adjacencies, of course, which I'm still going to use a dictionary for in this process. And since we're working with cycles, as I mentioned, we generally do this with a directed graph. So I'm going to set this up as a directed graph. And all that really means is that we only add the edge in one direction, right? So if u is in the self.adjacency, then we just add the v edge to the adjacency list, right? So we just depend on v. And then otherwise, what we do is we just set the value of u equal to the value at v, just like that. So we don't actually add the edges in both directions, just in the one direction here. And then what I'm going to do is I'm going to add my disjoint set, actual methods into the graph directly. So I'm going to have the find parent method. And all it's going to do is it's just going to do that same sort of setup. If parent at I is equal to I, then we return I. And then otherwise, what we do is we return the recursive call to self.findParent at parent and parent at I, just like that. So same sort of setup as we had before. And then we're still going to have our union or unite. I'll just call this union here. And it's going to unite together two different parts of our disjoint sets. So parent at x is going to be equal to y, just like that. Now, how do we use this to determine if a cycle exists? The idea is this. I'm going to set up a function called isCyclic, and it's just going to use our graph components. What it's going to do is it's going to set up the actual parent. And the parent, remember, is all of the different parents of items inside of our disjoint sets, right? So the way that we set this up is I'm just going to initialize this to have one slot for each vertice. So essentially, we're going to keep track of the parent of each vertice. And to initialize this, what we're going to say is that every single parent is going to be in its own disjoint set. So everything's in its own disjoint set to start. And then what I do is I say, we're going to iterate through all of the different vertices that we have. And for each vertice, what I'm going to do is I'm going to iterate through its adjacency list. And in its adjacency list, what I'm going to do is I'm going to find the parent of each node. So I'm going to find the parent of the actual node itself and then the parent of the adjacency. I'm going to store these as the variables x and y. So we're going to find the parent of each of these. And then what we're going to do from here is we're just going to check to see if the parents are the same as each other. If the parents are the same as each other, they're inside of the same set, which means that there is a cycle. If they're not the same as each other, then I'm just going to union together those two nodes. So basically what I'm saying here is I take a node and then I take something that it's adjacent to. I check if they are inside of the same set, and if they're not, I put them in the same set, right? And then I go to the next node and I do the same thing. And you'll see that as we continue merging those sets, if we had a cycle, there would be a situation where two nodes would be sitting inside of the same set as each other. So we would have been able to get back to where we started, right? So you see how that generally works to flow and find if something is actually cyclic or not. And then in the otherwise, we'll return false. Now, just to show you that this actually is working, we can construct a graph that has a cycle inside of it, right? So imagine a graph that goes from 0 to 1, and then we could go from 1 to 2, and then we can go from 2 to 0, right? So if you imagine this, you could go from 0 to 1, 1 to 2, and then 2 to 0. That's a cycle, right? Because we go from starting point all the way around to the starting point again. So we end and start at the same point, traveling all unique edges, right? So if I were to take a look at this and check to see if it has a cycle, it should generally tell me that it does. It should return me a value of true, right? So let's actually take a look and see if that ends up happening. And I'll see in here, oh, I was supposed to provide the number of vertices as well. There's 3 vertices, 0, 1, and 2 inside of this graph, right? So there we go. And now it gives us a value of true. Now, if 2 had gone somewhere else, like 3, that would now give us 4 vertices, right? Then we would have false, because it doesn't create a cycle. There's no way to get back where we started, right? So do you see how that generally is going to tell us whether we have a cycle or not? Now, this is really helpful for an upcoming algorithm that we're going to talk about, which is Kruskal's algorithm. In Kruskal's algorithm, we want to create something called a minimum spanning tree. The idea of a minimum spanning tree is basically it's a tree that is able to span all of the different nodes inside of our graph. And as we discussed in previous videos, a tree is a graph that has no cycles inside of it. So in order to make sure that the thing that we construct doesn't have cycles, we need a way of checking if a cycle would exist if we, added an edge into our graph. So this is a way of being able to ensure that we don't add cycles, is using this cycle detection. So we're going to take a look at that in the next few videos. Thanks so much for watching. I'll see you in the next one.